Okay, so we need to finish this argument about the quasi-free electron model. So let me, yes, there's a question.
Last time we completed the volume of our unit cell.
Yes.
Okay, here we are in this one space, I don't know.
Your what, sorry?
Okay, first.
We computed the volume of the unit cell. Yeah.
Because the reflection is one of our units of the unit cell.
Yeah, oh, you mean the normalization?
Yeah.
Okay.
Here we are in the reciprocal space.
Yeah, the reciprocal space.
Okay, because our reflection is like.
Can you speak a bit louder, please?
We are in the reciprocal space.
We are in reciprocal space, yes.
So the volume should be.
We carried out integrals in real space last time, right? When we normalized the wave function, we were carrying out integrals in real space, not in reciprocal space. Are you talking about the normalization of the wave function? When we normalize the wave function, the normalization was carried out in real space, right? It's the integral. Remember, k is a quantum number, is a label. Psi is a function of r, and there are infinitely many functions of r as a function of k, okay, for different k's. But the normalization is defined for each wave function, so this is carried out in real space. So what we have to do, we introduced this prescription for the normalization in which the integral is carried out over the unit cell. And we said that this has to be 1. And we also argued that this was not a problem because even though psi is not periodic, so in principle integral over the unit cell wouldn't make too much sense because it depends which unit cell you choose, for example, if it's not periodic. We argue that the square modulus of psi is periodic. Okay, so carrying out the integral of a unit cell is the same whatever unit cell you choose because it's the function is periodic. Okay, so that's the argument we use to use this convention. Okay. Why do you want to a Brillouin zone? We are integrating over space here, over real space. And this is the wave function defined in R3, the real space. There are many psi's for each one of the values of k's values of k in the Brillouin zone. So this is defined for k's belonging to the Brillouin zone. But the function is a function of real space. So it's defined in real space, the function. So this is the integral over the unit cell, not over the Brillouin zone. Does this answer your okay? Yes.
When we did one-dimensional band structure for one-dimensional for a free electron model.
Okay, sure. So we're talking about the one-dimensional band structure for the free electron model.
In the case we have 4 electrons.
4 electrons per unit cell. Yes, correct. Okay, that's a good question, yes. Yeah. So we have energy K plus pi over A minus pi over A. The first parabola, the second parabola, and then it continues. And then you say, okay, if we have 4 electrons, right? For 4 electrons, the Fermi level is there. So your question is, what is a Fermi vector? Well, in this particular, let's say, notation, convention, the Fermi vector is 0, because this is the point where the Fermi level crosses the band structure, the value of k for which the Fermi level crosses the band structure. Now, what shall I say? This is the case, of course, if we assume that there is an underlying lattice with periodicity A and so on and so forth. I mean, in principle, you can forget about the underlying lattice and treat a free electron gas just purely as a free electron gas without even introducing an underlying lattice. And of course, in that case, the values of the energies, you don't classify the values of the energy in terms of the Brillouin zone K, but you classify them according to your Q, like a free electron wave. And then you may argue that the correct value of the Fermi vector is actually this one. Okay? So I just want to warn you that there are two possible ways in which you can see the band structure of a free electron system. You can see the band structure of a free electron system assuming that there is an underlying lattice. This is the picture we followed. And we followed it because it is extremely important to use this picture if you want to then introduce perturbation to the free electron model. So in this picture, Kf is 0. No question about it. You may, however, wish to keep going with the standard free electron picture, forgetting about the existence of a lattice, forgetting about the existence of the Brillouin zone. And in that case, the parabola is a parabola that extends from minus infinity to plus infinity. And therefore, the value of the Fermi vector would be this one here, because that's the point in which you stop filling your electrons. In our notation, these parabolas are refolded inside the Brillouin zone, and therefore the Kf is 0. So it depends. It depends, depending on your on the kind of the convention you want to choose to describe your band structure. I have to say that this convention here holds only when you're dealing with a purely free electron system. As soon as you introduce any small perturbation, you introduce the presence of a lattice, this picture doesn't hold any longer. So you have to use this picture. So since we're dealing with solid-state physics where the band structures are never purely free electron-like, I personally prefer to use this one because I mean, you'll never actually have a situation in a real system where the Kf is larger than the size of the Brillouin zone. People might argue, well, how can you have a Fermi vector which is outside the Brillouin zone? This is not possible because our band structures are defined within the Brillouin zone. So, having said this, some people might still use the free electron picture to define the Fermi vector. Okay? So, in our classes, if we need to define something like that, I'll try to clarify which one I mean. Actually, I will always use this notation with Kf equal to 0 in this particular case. By the way, same for any kind of filling, even if the Fermi vector is, the Fermi level is here, right? Fermi level could be either this one or it could be this one, depending on whether you work with the Brillouin zone or you work in an extended zone. I personally prefer to use the Brillouin zone picture because this is more consistent with the realistic system. Any more questions? Okay, is that okay? Okay. So let me summarize quickly where we got last time. So last time we were trying to solve this quasi-free electron model. And the quasi-free electron model is defined by the Hamiltonian plus something that we, actually we put a minus here, V bar cosine of 2 pi over A R, in one dimension at least, okay? So we're going to just do the example in one dimension. And the assumption was that V was small. Small enough that we can treat this term as a perturbation over the free electron solutions. Okay, so we argued that on top of the free electron solutions, which are the unperturbed free electrons, the presence of a perturbation was causing almost nothing outside the points where there is degeneracy, because outside the points where there is degeneracy, the perturbation didn't do anything to first-order perturbation theory. Only second-order perturbation theory was there. While where there was degeneracy, we argued that this perturbation was split in the degeneracy to first order and was giving rise to two states out of this twofold degeneracy, which would continuously merge into the original states, the unperturbed states. And of course, because of K minus K symmetry, the same must happen on the other side. So the actual band structure in the presence of this small perturbation becomes something like that. And no longer with the degeneracy here. And with a splitting here, which we calculated to be equal to twice the value of the strength of the perturbing potential. We calculated, you remember, this 2 by 2 matrix, and we solved the problem exactly at this point. And we found that this is by the way, now that we know the solution, we can actually go back to the question of how small does V bar need to be in order for this to be treated as a perturbation to first order, as a perturbation to be treated in perturbation theory. Okay. Sorry?
The magnitude is not twice of V bar. I think it's this.
Oh, sorry, yes, because it was twice, yeah, sorry. It was twice V bar over 2, sorry. Yeah, correct. Thank you. Thank you, yes. If we write it like this, yes, correct. So the question now we want to answer is, in order for all this theory to work, that is, in order for this object to be a small perturbation over the free electron model, we didn't discuss how small we wanted V bar to be. Now we are in a position to do it. So we do it, if you wish, a posteriori, after we've solved the problem. We go back and we try to determine how small does V bar need to be in order for perturbation theory to be effective, to actually work the way it worked. So we use perturbation theory to first order, for example, at the generic point K. And we said that we can use perturbation theory, for example, here, under the assumption that the strength of the perturbing potential was small with respect to what? What is the standard, say, criterion that you use in order to determine whether a perturbation is small in perturbation theory? You compare the strength of the perturbing potential, say V bar, to what? What do you want this to be much smaller than? In case, I mean, you're talking about the general theory of perturbation theory, right? So we have a non-perturbed potential, a small perturbation. When can we claim that V bar is small enough that we can use perturbation theory? What is the condition that V bar has to satisfy, or the strength of the perturbing potential has to satisfy in order to be treated as a perturbation with respect to a non-perturbed potential?
It may be fine structure times the energy for the unperturbed.
The fine structure, sorry?
Yeah,
You're right, yes. Can you elaborate a bit more? What is the criterion? I mean, generally, right? It's not about this problem in general. It's about the general problem of dealing with perturbation theory. You have a small perturbation to an Hamiltonian, and you want to determine whether it's small or not. What do you look at?
it should be small compared to the unperturbed.
What unperturbed? Of what? Yes? The energy level, the difference between the energy levels, okay? So this is much smaller with respect to differences. Now I'm writing using standard notation, right? Between any pair of energy level of the unperturbed Hamiltonian, differences of energy levels. Of course, with the exception of those energy levels which are degenerate or whose difference is less than this, in which cases you use perturbation theory to first order, and you solve the n by n problem within that degenerate manifold. Okay? But the general condition for this to be valid is that for, say, a very large set of energy differences, this energy difference is large. For all the other ones, you can treat them in together as a degenerate manifold. But there must be a large number of EI, EJs for which the difference is, all the other ones, let's say, for which this difference must be large. Now, again, suppose we are at this K. The unperturbed eigenvalues were this one, and whatever. So what we want in practice to happen is that V bar is much smaller than, well, this energy difference, for example. But of course, this energy difference is different, different places of the band structure. We don't, of course, we don't want this to be valid everywhere, right? For example, here, it's clearly not valid when they become degenerate. In fact, that's where we use perturbation theory to first order to solve the problem. But everywhere else, we want it to be small. So the obvious scale of energy here for differences between eigenvalues at points where there is no degeneracy, what could that be, the general scale of energy? Let's forget about factors. What could the general scale of energy be for these differences? Here, 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 and up. But it's h bar over m a squared, right? For example, this one is pi square times this one. This one is 4 pi square times that one. In fact, we may even wish to put a pi square. It's probably more accurate. It's an order of magnitude, right, pi square. So this is roughly the scale of energy within numerical factors that characterizes differences between eigenvalues in our band structure. Okay, so this is actually, in our problem, the typical scale of energy is h squared pi squared over m a squared. Do we all agree with this? So that's the typical scale of energy differences in the free electron model with some numerical factors, 1, 4, pi, whatever, square root 2, or whatever you want. So we want the strength of this to be much smaller than this scale of energy, of course, except at those points where we are going to treat this as a degeneracy. Now, just as a very qualitative discussion, is this condition actually valid if V is the strength of the potential is something more realistic than this one? For example, our past examples of an external potential were the Coulomb potential, right? We had this Coulomb potential which we approximated with this cosine, but clearly this is an approximation. We actually argued that this approximation works well because of screening, but let's take the extreme. I mean, let's take a completely unscreened Coulomb potential. So let's assume that potential is what we, for example, used at the very beginning of our, so a series of Coulomb potentials centered at the different sites. I'm just making some very qualitative arguments now. Well, it's difficult to say, to claim whether this potential is much smaller than this one in that particular case. I mean, in the case of a cosine, it's easy because this potential has a maximum strength of V bar. But for a Coulomb potential, the Coulomb potential is arbitrarily large, in principle, arbitrarily large. It can diverge to minus infinity, right? So it's actually never true that the potential is always smaller than the differences between the energy. It depends how you evaluate the potential. In fact, the correct exercise to do is not to take the generic strength of the potential, but to take expectation values of the external potential on any pair of unperturbed states. If you go back to your perturbation theory criteria, you probably remember that here we are actually writing something not fully correct. We should be calculating expectation values of this potential with respect to all the possible pairs of unperturbed states. And that is the criterion that gives us whether the potential is small enough or not. So here we're just using a generic strength by using the constant in front here. Certainly we would be in trouble for the Coulomb potential. The Coulomb potential, we would have to calculate the expectation values because the potential diverges in some points. So clearly this condition is never satisfied, or at least is not satisfied at the points where it diverges. Yet, I mean, let's introduce a scale of energy for the Coulomb potential. We are not certainly interested in the peculiarity of this divergence. The divergence is just a single point and is not really going to do any particular harm to the problem. We know it's a Coulomb potential, so we know it's something of the order of E squared. And let's introduce just a characteristic length here. So I'm now trying to argue what is the strength of the Coulomb potential as a number. So it's certainly E squared. And the typical length of the system, the only length actually, is A here. So let me just define the strength of the Coulomb potential as E squared over A. It's the only way I can construct something similar to a Coulomb potential with the constants that I have available. So if it's not this, it's going to be a numerical factor times that, the real strength of the Coulomb potential. Instead of using this, I'm using the full Coulomb potential. I hope you understand that I'm really going to make I'm following a very qualitative argument here. I'm just want to somehow give you a hand-waving idea of whether I can or cannot apply this kind of theory in general, not just to this particular kind of potential, but whether in general, if I deal with a Coulomb potential, this term is actually going to be much smaller than the kinetic energy term. So the question then becomes, is this term much bigger than this one or not? Right, in a solid. So is it true? How can I compare h squared over m a squared pi squared with e squared over a? Is this much bigger than this one? Is this much bigger than this one? Is the opposite? I mean, what can we say about it? Well, if I actually compare properly and I bring A to the other side here, the actual comparison is whether A, if I bring it there, is how does A compare with, well, let me assume that, let me check whether this is much bigger than that, okay? So to do something concrete. Checking whether this is much bigger than that is the same as checking whether A is much smaller, I'm bringing A to the other side, is much smaller than m e squared, pi squared. Right? But this one, it's a Bohr radius. So here we're talking about something which is 10 times the Bohr radius. Okay? Now the Bohr radius is half an angstrom, so 10 times the Bohr radius is 5 angstroms. That's more or less the distances between atoms in solids. 3, 4, 5, 2.5. I mean, we are in that range. So what I'm trying to argue now is that if I use the generic strength of the Coulomb potential, we're actually in the situation in which the potential has the same strength as the kinetic energy, unfortunately, for a large class of systems. So this condition does not hold, because A is of the order of 10 times, 5 times, 4 times, 10 times the Bohr radius. So in practice, for a realistic system, if I consider the pure Coulomb potential, the kinetic energy has more or less the same strength as the potential energy in my problem. So I cannot, in principle, use perturbation theory. However, and now we go back to the discussion we made at the very beginning of our free electron model picture, there are systems for which the potential seen by the electrons is much weaker than the Coulomb potential because of screening. Because the Coulomb potential, due to the nuclei, is almost completely screened by the fact that the electrons rearrange. And therefore, the final result is something which is much, much weaker than the original Coulomb potential because of the fact that the electrons, all the other n-1 electrons, screen the presence of a nucleus, seen by each single electron. So each single electron sees the nucleus, but it also sees all the other n-1 electrons. And these n-1 electrons go to places, are attracted by the nuclei, and therefore reduce the charge of the nucleus, the effective charge of the nucleus seen by each other electron. So as a matter of fact, the actual potential in some systems, at least, because of screening, the strength of it is much smaller than the strength that we estimated based just on the Coulomb expression. All right? But the important point to keep in mind is that the characteristic energy that we need to compare our potentials to is the kinetic energy for that particular system, which is easy to evaluate if once you know the lattice spacing, the distance between atoms in your system. Okay. End of the discussion about how small. So now we have a criterion to small. We know what that means, right? We know V bar must be much smaller than H bar pi square MA square, which is the case only for some systems, not for all of them. But there are systems for which this kind of approach is actually quite valid. I mean, you can actually use it, and it gives a pretty good description of the band structure for some systems. There are systems, in fact, for which not only this approach is valid, but the fact that here, where the difference between the free electron model and the quasi-free electron model, which is primarily here, these are the two regions where the two models differ, is actually almost irrelevant. Suppose you have a system with only one electron per cell. One electron per cell, you're supposed to fill only half. Right? Your Fermi level is here. So your field states will be here. Now you clearly see that in this particular situation, one electron per cell, the fact that here there is a splitting doesn't really affect at least the field states, or it affects them only to second order in perturbation theory. So the class of materials with one electron per unit cell, and for which this is a decent approximation, behave almost like free electrons. Because even if this is not, say, even if the perturbation becomes, say, important, like the splitting here, the states that are filled are far from the regions where the perturbation is important. It's a very particular case, right? Because as soon as I go to 2 or 3 electrons per cell, I start filling the bands in such a way that this becomes filled, right? So it becomes important to know the details of V bar here. If I'm below this point, I don't even need to know V bar. I can forget about V bar. The system behaves like a free electron system, even if V bar becomes relevant to discuss the band structure. Because those points are located at k points where perturbation theory to first order gives me 0. And only perturbation theory to second order becomes relevant. So 1 electron per cell is a case in which not only I can typically work with perturbation theory, but even if the perturbation is not that small, the fact that my relevant electrons are here implies that I can essentially forget about the perturbation. In fact, if you take all the elements of the first column of the periodic table, lithium, potassium, sodium, rubidium, they all behave almost like, differences between the free electron model and the behavior of electrons in those systems are typically small, and they're treated like perturbations of second order in perturbation theory. But we need to be along the first column of the periodic table, where the number of electrons, of valence electrons per cell is 1. So it's very, particular case, but it's a case in which the theory, the free electron theory actually, not only the quasi-free electron theory, but the free electron theory works pretty well. Okay, so we are in the first column here. So we are lithium, whatever, potassium, sodium, cesium, rubidium, and blah, blah, blah. Well, actually, that's it. By the way, they all crystallize in crystals in which there is one atom per unit cell. If they, by any chance, crystallize in systems with 2 atoms per unit cell, we wouldn't be able to make the same statements. But we can make these statements because we know that they crystallize in systems with 1 atom per cell. So there is one electron per atom, but there is 1 atom per cell, and so there is 1 electron per cell. Now, let me consider now 2 electrons per cell. We go to the second column of the periodic table. Magnesium, beryllium, calcium, barium, and all these alkaline earth materials. Almost all of them crystallize in structures with 1 atom per unit cell. Some of them take the HCP structure. But in general, you can say that they crystallize in structures with 1 atom per unit cell. So we have 2 electrons per unit cell in those systems. Now, what would you expect out of this consideration? Well, suppose, of course, that the quasi-free electron model works for these systems. If you have 2 electrons per cell, you fill completely the first band, and that's it, and you're done. So the Fermi level, whatever that means, is here, and there is a finite gap of excitation between the last occupied state and the first unoccupied state. There is an energy gap given by V bar. So if I now have 2 electrons per cell, I'm here now. So this is the Fermi energy for 2 electrons per cell, right? The system has a gap, has a finite gap. So according to the discussion we made a couple of lectures ago, this is what we would call an insulator, because there is a finite gap of excitation to excite electrons from filled states to empty states. For anyone, by the way, right? Because even if I take an electron that stays here, all the other states are filled. So the first excitation is actually here. Or I can go up. So any excitation has a finite energy. There are no excitations with vanishingly small energy in this problem. So in principle, systems like that should not be metallic, should not conduct electricity. We'll see later on why, again, the fact that there is a zero gap implies conductivity. But in general, we already defined systems with zero gap as metals and systems with finite gap as insulators. So we could, in principle, conclude, if this picture was correct, that this is the system should be insulator. In fact, unfortunately, if you take pure magnesium, pure calcium, pure barium, pure beryllium, no, it's an insulator, but beryllium is the only one. All the other ones are metallic, behave like if they were not really free electrons, but they behave like good metals. They conduct electricity. So what's happening? What's wrong with this picture? Well, of course, you may argue the quasi-free electron model perhaps doesn't work for these systems. This is actually not true. The quasi-free electron model works not so badly for these systems. What's wrong with respect to our considerations is that these systems are three-dimensional systems, not just one-dimensional systems. So let's try to imagine what happens in 3 dimensions now, okay, or in 2 dimensions at least. Okay, so here we have, instead of having a single parabola in 1 dimension, we have a parabola in 2 dimensions. We have at the edges of the Brillouin zone, at the faces of the Brillouin zone, instead of having just at the point, we are going to have at the edges of the Brillouin zone, we have these gaps that open around, right? You are in 2 dimensions now. So you have, for example, a 2-dimensional Brillouin zone here, and you have gaps opening at the border, at the edge of the Brillouin zone. But the way this window opens may not be necessarily the same. Suppose that the Brillouin zone is longer in this direction, for example, than in this one. The parabola here would go up, up, up until this point, and then there is a gap. Okay? Which means the value of the gap, the position of the gap, and the strength of the gap might actually be different depending on which point we are at the edge of the Brillouin zone. Okay? Do you see this? I mean, this is now the 1-dimensional picture, but you have to see this in now 2 dimensions. Define K in 2 dimensions. We have a square here, and we have the edge of the Brillouin zone going all around the square. Now, because the size of the Brillouin zone is not necessarily, if it is a square, of course, my argument would not be completely true. Although it would still be true, because if I move along the diagonal, think along the diagonal of a square, by the time I reach the edge, I had to go square root 2 times longer than if I go along the Cartesian direction. So my parabola, if this is square root 2 times longer, is going to be twice as high. The point that I reach at this edge, at the corner here, is going to be twice as high as this one, because it's square root 2, right? So the K square is twice. So you immediately see that if I have a more than 1-dimensional system, the position of this gap and the height of this gap might change depending on where there are different places in the Brillouin zone. So now, suppose I have to fill with 2 electrons. If the gap was everywhere at the same height, it would be simple. I just take a flat line, flat plane, and I have a gap. But if this starts to go up and down, well, I have to come to some compromises, right? There will be points in which the gap is above. There will be points in which the gap is below, right? And so therefore, the system is not necessarily an insulator. There will be points in which the Fermi level is crossing the bands. All right? So the reason why systems in the second column of the periodic table, again, magnesium, calcium, barium, and all these are still metals, in spite of the fact that the free electron model, the quasi-free electron model, works pretty well, and the quasi-free electron model would predict an insulator in 1 dimension. In more than 1 dimension, this is not necessarily the case, even if you are dealing with an ideal quasi-free electron model, just because the size of the Brillouin zone is necessarily not just it's never actually a circle. So the position of the gap is never exactly at the same point around the edges of the Brillouin zone.
So
Yes?
what if we consider perturbation in second order vector?
In second order in perturbation?
Yeah.
Oh, in here?
Yeah.
Oh, okay, that's going to be your homework. Okay. All right? We'll discuss it next time if you wish. It's going to be your homework.
Okay.
All right. Let's see. Yes, that's the last thing I wanted to mention about this quasi-free electron model. I need to go back I need to refresh how we calculated this splitting. Let me refresh. So we had two wave functions. One was 1 over square root of a e to the I pi over a r, and the other one was 1 over square root of a e to the minus pi over a r. I'm sure you'll find this in your notes. If you go back to your notes, you'll find that the two states that we identified as degenerate at this point are given by these two expressions, right? And we constructed the 2 by 2 matrix consisting of calculating expectation value of psi 1 and psi 2 on the perturbation. And I'm sure you remember that we got something like, what was it, minus v bar over 2, minus v bar over 2, and 0, right? Oops, no, sorry, the opposite. Sorry. 0, 0, minus v bar over 2, minus v bar over 2. This was the 2 by 2 matrix that we identified as. Now, without going through the mathematics, this is exactly the same matrix we found for the bonding anti-bonding state. You might remember. In fact, even the signs are the same because this is 0 and this, well, in that case it was E naught. But that's just an offset of the energy, right? If you change the elements in the diagonal by a constant, it's just an offset of the energy. What's interesting is that the sign of the off-diagonal elements is negative. And you might remember that in the case of the bonding anti-bonding state, we had T here, and T was negative, or at least we argued that in most cases it is negative. Because we used actually the fact that T was negative to find the solution. So if you remember, the two solutions here were psi plus equal to 1 over square root 2, psi 1 plus psi 2, and the bonding one, that's the bonding solution, which is the one with energy 0, right, the diagonal, minus V bar over 2. And then we had the psi minus solution, what we call the anti-bonding solution. Oops, no, phi 1 and phi 2, whose energy is 0 plus V bar over 2, right? I mean, I already used this statement when I argued that the gap was V bar. I just want you to remember that the actual solutions were the one with the positive sign, the one with the negative sign, and if V bar, I mean, the object here is negative, the one with the lowest energy is the one with the plus. You simply need to go back. It's just the mathematics. It's nothing to do with the physics here. We're just solving this 2 by 2 matrix with the negative element in the off-diagonal. You go back to your notes and you'll find that the solutions are given by this. In that case, it was the two atomic orbitals in site 1 and site 2. Here we have two different orbitals, but the mathematics is exactly the same. I want to get to this point because I want to comment now on the charge on the where are these wave functions. I mean, like we discussed in the bonding anti-bonding state, we discussed that psi plus had an accumulation of charge in the middle of the bond, psi minus at the 0 at the center of the bond. What's going to be the shape of these functions now in our problem? Right? So the problem, of course, let me re-plot it here, is the problem of an oscillating potential, V of R, and the potential is given by something like that. Again, but, I mean, for the presence of an offset. So psi plus, for example. Psi plus is psi 1 plus psi 2. Psi 1 plus psi 2. This plus this. What is this? Cosine, right? So psi plus is the cosine with some constant. Cosine of 2 pi, sorry, pi. Pi over a r. Psi minus, there's a minus, so this is going to be the sine. Now, what I'm interested in is actually not really just the wave function, but it's the square modulus of the wave function. This is what tells me where the charge is, where the probability of finding an electron is. So I have to take the square of this. Now let me plot now in yellow psi plus. Cosine square of pi over a r. So at 0, it is maximum. At r equals to a, at r equals to a over 2, that is halfway, it's 0. At r equals to a, it's cosine of pi minus 1, but it's square, so it's 1 again, maximum. In fact, this is this function here, okay? So this is psi plus. Let me plot psi minus sine squared. So it starts with a 0. Maximum at r equals to a over 2. So here, and 0 again. So it's the same, of course, by just translated by half a period. So this is psi minus. Notice that we started the two original unperturbed wave functions. If you took the square of them, the square of the wave functions, the square modulus of the two wave functions, they were both flat everywhere. We have built a linear combination of the two actually linear combinations, such that the charge is now completely split. Psi plus is the yellow one, has the maximum at these points, and the pink one, psi minus, is instead peaked half a period away. Of course, if you take the sum of psi plus squared and psi minus squared, you get again a flat distribution, because it's just a unitary transformation of this pair of wave functions. But if you take the two separately, we go from a flat distribution for both, flat charge density, to something which is now characterized by a well-defined distribution of charge. And the distribution of charge is actually interesting, because the one that actually has the lowest energy, this one here, by the way, remember, these two solutions are the two solutions at pi over a here. So we're talking about psi plus as being this solution, and psi minus as being this solution, right? Separated by V bar. And psi minus is now located primarily where the dips of the potential are, and vice versa, psi minus, the other one, the one which is higher in energy, is located precisely where the maxima of the potentials of the potential are. Okay? So, what is the, let's say, the final thing to notice here? The presence of the external potential, that is of this corrugation, the white potential here, is such that it is preferable for electrons to sit not just everywhere, but it's preferable for them to sit close to these points, because this is the point where the potential is lowest. So obviously, once you build a solution to the problem, the solution with lowest energy is the one which is located primarily where the minimum of the wave function, of the potential are. On the other hand, The solution with the higher energy is the one located where the maxima of the potentials are. So it's just a way to visualize something which is probably very obvious to us, that perturbation theory must split the levels in such a way to favor some and disfavor others. And obviously the ones that are favored are the ones that are sitting at positions where, in order to take advantage of the fact that the potential there is lower. Okay, so it's a bit like the discussion we made for the bonding and anti-bonding state. The state that was taking advantage of the presence of the two atoms was the bonding state, and it was gaining some energy. And the other one was, of course, instead losing energy by having the opposite linear combination of the two original orbitals. Let's see. No, I think we can stop here as far as the quasi-free electron model is concerned. And now we're going to say something more general about band structure. So is there any question now about this? Yeah.
How the electrons screen the potential in this configuration?
How do the potentials screen the other electrons? How does...
In this configuration.
Okay, fine. Let me discuss. This is interesting, yes. Now, let me discuss the case, for simplicity, the case in which you have 2 electrons per cell. If you have 2 electrons per cell, that's actually the optimal situation to discuss what you're asking, because for 2 electrons per cell, this state here is filled, and this one is empty. That means that out of something which was completely flat in terms of charge distribution, you're now constructing a corrugation of your density. If you look at the total density of your system, the total density of your system, of course, is given by the sum of the charge densities of the square moduli of the wave functions of all the field states. These states here are unaffected, so they're still plane waves, so they're just flat. But as soon as you come closer to the edge here, to this point, this state here is going to be corrugated, psi plus, right? Okay, so the overall charge of the system, of all the electrons taken together, is going to have a small corrugation corresponding to the yellow one, right? Because there's going to be a little bit of accumulation of charge close to the nuclei. What does this mean? That if you take the external potential, which is V bar, and you sum to it the contribution due to the repulsion due to the other electrons are sitting precisely at points where the potential is attractive. And because they're sitting there, they are going to make this point less attractive for all the other electrons. Okay? So, if anything, this charge distribution is going to make the potential even weaker than what it was at the beginning. So this is actually where you see this screening in action. Here we haven't assumed anything about screening. We just say we have an external potential, but you clearly see that if you fill the electrons properly, the electrons prefer to go to places where the potential is attractive. And if they prefer to go to places where the potential is attractive, they will be repelling for other electrons to go there, right? So the potential overall will become even less attractive at those points. So screening in general is something that always goes in the direction of making the corrugation of the potential smaller. Because where the potential is deep, the electrons will go, and if the electrons go, will repel other electrons. Okay? So overall, if you have an external potential, you throw electrons into this potential, the actual potential seen by each one individual electron due to the original potential plus to the potential due to all the other electrons is much weaker than the original potential. Okay, so that's actually the concept of screening, which you actually see in action here, because at least for 2 electrons per cell, you clearly see that the charge distribution, the resulting charge distribution is going to accumulate at points where the potential is attractive. And so if you add up then after, in addition to the white curve, you add up the repulsion due to the yellow curve, you'll see that this can only make this corrugation smaller and smaller and smaller.
One more question.
Yes?
When we see the profile of the energy with K,
Yes?
and then is K is, still K is just a quantum label.
Right.
And then at K is equal to pi over A and at K is equal to minus pi over A, the energy is, higher compared to the
Yes.
rest. Now, what does it mean? Physically, I don't know.
So you're asking, you say, this is the band structure. You have a band structure which has energies at pi over A and minus pi over A, which is larger than energies at all the other points. What does it mean from a physical point of view? I'm not sure it means too much. In addition to what it means already in the free electron model, it is correct to say that this is not a real physical quantity. But if you go to the free electron model, this K is actually a real physical quantity. It's the momentum. Okay? And the larger the momentum, the larger the energy. Okay? So even though I'm the first one to tell you, don't think of it in terms of a momentum, well, in this particular case, I would say, relax a little bit and consider that there is a free electron. If you think of it in terms of the free electron model, you're allowed to do it as long as you make sure, make sure that you are convinced that this is not a momentum. You can now go back a little bit and say, okay, let's consider it for a minute like a momentum in some case. So from a physical point of view, this is a reminiscent of the fact that there is an underlying free electron model. And in the free electron model, this has a physical meaning. It's the momentum, and therefore. Certainly, if you get to this point, you're lost if you continue working in terms of free electron model. For example, that's actually an interesting question. What is the momentum of this state psi minus? Now, you started from two states, one propagating with a momentum in this direction and one propagating with a momentum pi over A in this direction. Okay? If we were thinking of them as plane waves. Now you construct a linear combination. You're here, you construct a linear combination, which is a linear combination of the two. What is the actual momentum of this state? Momentum in quantum mechanics is a well-defined concept, right? So you can calculate it. Momentum is, well, in one dimension, it's IH derivative with respect to R. I always forget whether it's a minus or not. There's no minus, right? I guess. There's a minus. Okay, sorry. Yeah, but it's enough to do this. So, can we calculate the momentum of psi plus, for example? No, sorry. Psi plus. So this is psi plus, not psi minus. Sorry, psi plus. Well, it's the momentum of psi 1 plus the momentum of psi 2, right? If I take, do I need to do all the calculation, or can you just? So it's pi over A, well, h bar pi over A minus h bar pi over A. So this is the momentum of 1, and this is the momentum of 2. If you don't trust me, you just do the calculation. You take the expectation value of this quantity, of this object with the pi. There are, of course, the cross terms when you do the expectation value, but they vanish. You can show that they vanish. So it comes out like this. So the actual momentum is 0. Obviously, right? I mean, psi plus is the cosine. It's the stationary wave. It's not moving. It's the cosine. So it's a sum of two waves propagating in opposite directions. So the momentum of this function is 0. It carries no momentum physically. So you see, I already found a contradiction with respect to your argument of the free electron waves, because I'm here and I was expecting a wave with some velocity, with some momentum, and I find something with 0 momentum. Has all the momentum transferred to psi minus, perhaps?
Yeah.
Maybe. That's the sign. Does it change? No. It's just, again, the linear combination of two waves with the opposite velocities. Sine is also a stationary function. It carries no momentum. You can calculate it, right? It's not probably obvious, but just calculate it. Take this function, take this expectation value with the momentum operator. Trust me, it's a sign, so it's not propagating, because it's a combination of two waves going opposite. So the momentum, even of the momentum of psi minus is 0. Okay? So you have transformed a problem in which the wave functions had some definite momentum and therefore some energy, according to a free electron picture, into something which is 0 momentum, both here and both here. They stopped suddenly. So you see that you have immediately lost your free electron picture once you get to that point. I agree with you that if you are far from here, then you can still think in terms of free electrons. But as soon as you get close to this point, everything is completely changed, to the extent that the wave functions don't carry any momentum any longer. They just stop. They're just stationary states at that edge. Okay? So if you, for example, calculate the velocity of the momentum as you go along this K, for example, here it's 0. Here it's growing, of course, it's growing linearly with when you move away from here. But at some point, you see it decreases again, it goes back to 0. Sorry, that's something I'll probably have a chance to say in a couple of lectures. The velocity of a wave function is proportional to the derivative of the band structure. That's a very powerful and interesting concept that we will elaborate later on. So without having to calculate all this, you can immediately say, if you look at a band structure like this, if you want to know what is the momentum of a wave function, you just look at the slope of this of the band structure. The slope of the band structure tells you what is the momentum of a particle. So by the time you get to this point, this must be flat, because the thing has to be periodic. So by the time you get it's flat, and therefore 0 momentum. So you could have predicted it without calculating that the momentum of this wave function was 0. But in any case, if you move away from here, momentum grows, and then it declines again. It goes down to 0 once you get to this point. So it's definitely not like a free electron. Any more questions? Yes? Yes.
When we were discussing when we have to, in the second line of the radical table.
Right.
Then now for me it becomes a bit difficult to understand how can we define an insulator if we define into relations.
Okay, so the question is, we were looking for insulators, and for example, in the case of 2 electrons per cell, we realized that this cannot be an insulator because, or at least it can be not a metal, let's say, because it depends on the shape. So how do we look for insulators? Now, the first answer to this question is that, well, if the system is a real insulator, very likely this model is not going to work, the free electron model. The free electron model works for systems which are close to metal, to be metallic, because the free electron model is a metallic system. Okay, so the first answer to your question would be, well, you're certainly starting from the wrong model. If you want to describe an insulator, this is not a good starting point for sure. However, you might still want to use this model, and perhaps, this model might work for an insulator as long as V bar is sufficiently large. If V bar is sufficiently large, suppose V bar is, say, like this. Now, of course, the fact that this is a perturbation is not going to be valid any longer. But let's forget about these details, little details. Assume we get to the end of the story and we have a V bar which is that large. Now, at this point, whatever you do, if V bar is sufficiently large, the gap is going to be quite robust. So it's going to, even if it fluctuates, if V bar is sufficiently large, you have a real gap. But that also tells you that V bar needs to be very large in order for this to yield an insulator. And that already tells you that perhaps your starting model was not a good one. Okay. Yes?
When we calculate, using the perturbation theory,
Yes.
we didn't consider the degeneracy of minus k and k.
Yes. Okay. You're right. Yes, that's a good point. You're right. I should have mentioned this. Now, we consider this degeneracy at the edges. okay? Because we actually did consider, at the end of the day, the k minus k, even though we did it in a very sophisticated way, because we actually said that if you're exactly at this point, the other point doesn't exist, because either I include one edge or the other one at the edge of the Brillouin zone. So if I'm actually at the edge, I don't have any degeneracy due to k minus k, because if I am at the edge, either I take k or I take minus k. I cannot take both. So that was a fake degeneracy. But your argument could be correct anywhere else, right? If I'm here, for example, I have another state which is degenerative here. So how come I forgot about this degeneracy when I constructed my wave functions? Now, that actually goes back to probably the first discussion we had when we introduced the concept of bands and the concept of h of k, if you remember, and when we introduced the perturbation. I told you that we solved the problem originally assuming that k was a good quantum number, right, by using our h of k Hamiltonian for a specific k. Then we added the perturbation to this. Now, the perturbation, if it's a good one, has the periodicity of the lattice, okay? Which means k is still a good quantum number. And if k is still a good quantum number, I don't need to couple Hamiltonians at different k's. I can apply perturbation theory within the same manifold, the same value of the quantum number. Okay? I don't need to, if the perturbation has the same, say, symmetry as the Hamiltonian, I can work within the manifold of the solutions given by the quantum numbers of this Hamiltonian. If you wish, we could actually even show that the coupling between these two. Let me see another way to see this. Okay. Unfortunately, I need to somehow forget about the normalization, because the normalization is not going to work in this argument. But let me take two generic plane waves, one with, say, plus IKR, and another one with minus IKR. Okay? So this is psi 1 and this is psi 2, and they are psi 1 and psi 2, a generic K, with K being a generic 1. I want to see what couples them. So if I want to see what couples them, I need to check what kind of perturbations V of R okay. Now this gives me, I'm going to be not very mathematically very strict, but I hope you follow the qualitative discussion. So if I want the two plane waves to be coupled with k minus k, which are degenerate, I need to find the potential that gives me a non-zero matrix element between the two, regardless of what the normalization here. This product, this integral must be non-zero in order for them to be coupled. But this, if you notice, is exactly the Fourier transform of V of R. It's V tilde at 2k. By V tilde, I mean the Fourier transform, the Fourier component of V at, say, in the reciprocal, for vector 2k in the Fourier transform space, right, in the reciprocal space. So the same, this is equivalent to say that this must be different from 0. Now, if you have a periodic object, a periodic potential, the only Fourier components, for example, this one has only one Fourier component, at 2 pi over a. Okay? In fact, so this one has only v bar 2 pi over a different from 0. All the other ones are 0 for a cosine, because the Fourier transform of a cosine has a single Fourier component. Well, a minus 2 pi over a, of course. So you see, the only k that I can couple are the ones corresponding to pi over a. If I want this to be non-zero, the only k that satisfies this non-zero here is k equals to pi over a. That explains why I could do it there. But let me be more general. Suppose I here have a generic perturbation, not just v tilde, even a generic one. If it's periodic, you can actually show that the only v tilde that are non-zero are all the v bars that are of the form 2 pi n over a for a generic periodic potential. So 2k must be equal to 2 pi n a. That is, k equals to pi n a. But again, k must be in the Brillouin zone. So the only n that satisfies this is n equals to 1. All right? So that's another way to see this. But otherwise, we can use the simple argument. So this is the other way to see it. If you want to couple these two wave functions are never coupled by an external potential which is periodic, unless k and minus k are at 2 pi over a from one another. But then we've done it already. Okay. Let's see. I'm wondering whether it's worth now starting with this new discussion with only 10 minutes left. Probably not. So let me just give you the homework now. So next time we're going to start with a more general discussion about band structures and their implications. So for the time being, we stop here. We have done the quasi-free electron model. We have analyzed a number of consequences and properties. What I would like you to do as a homework now is solve and discuss the problem with four pi over a r. Okay? What is the shape of this potential? If this is A, it's a potential that behaves like this. Okay, that in each A oscillates twice. Right? It's 4 pi over A. So there are two oscillations for every A, for every period. It is a periodic potential because it has the periodicity of the lattice of A. It is actually more than that. It has a periodicity which is twice that of the lattice, but that's okay. It has the periodicity of the lattice. We can assume this to be a small perturbation, so we're going to assume that V bar is small in whatever sense we discussed already. And of course, this potential is going to modify the band structure in a different way. So I would like you to discuss how does this potential modify this degeneracy as well as this degeneracy. Okay? So discuss and calculate, of course. So more or less do what we've done here, of course, with the exception of all the final considerations of the wave function. It's just enough for me that you get to the point where you draw qualitatively the band structure. Okay, I don't want you to analyze psi plus and psi minus and all this the things that we discussed today. Discuss how V of R splits the genera C's. The genera C's at pi over A and also at 0. That is this point here. Yes.
When we write here 4 pi over A, we are saying we have 2 electrons per unit cell or 2 atoms?
No, actually, I mean, if you wish, you can discuss this. You can discuss. I mean, when does this perturbation affect your problem or not?
Yeah, because we usually represent the potential profile of the nuclei by this, right? And then we have now two loss points, and
Yes.
they represent something that creates an attraction.
Yeah, this is the potential creates an attraction here, 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 and so on and so forth. Yes. So it's going to affect.
If we have 2 atoms.
If you wish, you can see it that way, yes. Feel free to discuss. I mean, if you want to add something, I mean, discuss it. Again, homeworks are not graded, okay? So feel free to possibly try not to do it too much together because, I mean, it's, or try to do it first yourself and then perhaps ask help or discuss it. I mean, I encourage discussions, if you wish, among each other. So I'm not going to grade the homework. I'm going to discuss it, so we're going to discuss it probably not next time. Let's do it by Monday next week, okay? And Monday we discuss it together. Okay? No questions? Nothing? All right, so we continue on Wednesday.